Thank you very much for the introduction, and I want to thank the organizers. Adekunle, Peter, thank you very much for bringing us all together. It is a wonderful workshop. I'm enjoying quite a bit. So we have just heard from Will what happens to the dynamics if we use a tri-layer artificial spin-ice system. I'm going to use a different approach. I also will use a pseudo 3D 2.5D system. And I will show you what happens if we pattern an artificial spin-ice on top of a thin film underlayer. In particular, I will discuss the vertical dynamic spin-wave mode coupling in the system and the associated dispersion in that system. So before I get started, I want to introduce the team and the collaborators. This is my group at the University of Delaware. The work on nanomagnetics with artificial spin-ice was initially done by my former graduate student Mojtaba Tashipur-Kafash and my former postdoc Sergi Landines. And this work is now being continued by Ronak Sultana, a graduate student in my group, and Vinay Bhatt. The results that I'm going to show you today are a result of a very fruitful collaboration with Gianluca Gubbiotti and Federico Monticello. So most of the experimental results that I will show you today were done in Gianluca's lab. And Federico provided us with essential micromagnetic simulations, which really tremendously helped us understanding the experimental results. So we are also very grateful for financial support by the US Department of Energy and the National Science Foundation, who support our efforts in understanding dynamics in artificial spin-ice systems. And particularly DOE supports our efforts in these kind of 3D systems. I also want to acknowledge NFFA for providing us access to facilities at Perugia. All right, so my group is interested in creating functional magnetic devices. And we want to control spin wave properties at the nanoscale. And of course, what comes to mind is a magnetic crystal, where we periodically modulate the magnetic properties in space. And this results in opening of band gaps in the dispersion because spin waves undergo Bragg reflection. Now, magnetic crystals have been studied for a long time. This is some work by Adekunle's group, published in APL about 15 years ago. This is a 1D magnetic crystal with two dissimilar ferromagnetic materials patterned into stripes. And I've taken here the experimental results from this APL article, so you can clearly see these band gaps in the dispersion. Now, we were thinking about how can we translate this into 2D, and one way to achieve this is to use an artificial spin-ice, and I view them as a 2D or 3D magnetic metamaterial. So typically, these islands here in our strongly interacting array of nanomagnets have sizes of a length of about 300 nanometers and a width of less than 80 nanometers. So typically, we choose the thickness to achieve a single domain state, so have a macrospin state. Will talked about earlier what happens if you play with the aspect ratio. Then you can also host vortices, and it's important, especially for neuromorphics, that you can have this bistability between vortex states and macrospin state. In my talk, I'm going to focus only on the macrospin state in these elements. Now, if you have these kind of macrospins in a square system, you get 16 possible configurations. Type 1 and type 2 are low energy states, and type 3 and type 4 are higher energy states. You make these samples using electron beam lithography, E-beam evaporation of ferromagnetic metals such as nickel iron, cobalt iron, or cobalt iron boron, followed by a lift-off process. And you can see here a scanning electron microscopy image with the scale bar. And I'm highlighting here one vertex. We can also characterize the magnetization of our systems, for example, using MFM. This is work done in collaboration with Paul Davis's group at Boise State University. And from this MFM contrast, you can see this is a type 2 ordered state. Now, the idea of using artificial spin-ice systems for magnetic applications goes back to a theoretical proposal by Sebastian Klieger and co-workers published about 10 years ago in PRL. And what they did is they used micromagnetic simulations, and they introduced monopole, anti-monopole pairs in an ordered type 2 background that you can see over here. And what I found then is, depending on the number of monopole, anti-monopole pairs and the length of the strings connecting them, certain modes appear in the resonance spectra. And this really piqued our interest, so we made these samples, and I'm showing here some early work we've done. So you see the rich mode spectrum that we observed in broadband ferromagnetic resonance, and by now it has become clear that we can use FMR in microwave spectroscopy to fingerprint the artificial spin-ice state. Okay, so my group is interested in tuning these interactions of magnons in nanomagnetic structures. Everything I've showed you so far is 2D, so I'm going to give you a brief overlook what we have done in my group. So we started off with understanding the essential building blocks, each individual element that make up the entire lattice, and how each element contributes to the spectrum. And we found a superposition principle of the modes. We also looked into a bicomponent artificial spin-ice lattice with two dissimilar ferromagnetic materials in the two sublattices. In the vertical and in the horizontal elements are different ferromagnetic materials. And in this case, the superposition principle breaks down. So we observe here emergent dynamics in this kind of bicomponent artificial spin-ice system. Similar approach was done by Will Branford's group, where they played with the shape anisotropy to achieve the same goal, essentially. We also looked into nonlinear magnon-magnon interactions in these networks. So we found here that there's an orthogonal coupling between the vertical and the horizontal sublattice sites if you drive the system in the highly nonlinear regime. And then from an applied point of view, there was this really beautiful work by Jack Gartside and Will Branford and co-worker, where they showed that we can use this hysteretic behavior of the artificial spin-ice system for neuromorphic computing. So all of this is 2D, and there were some initial proposals, micromagnetic simulations, essentially. The first one by Itsuya Koka, Sebastian Klieger and co-workers, where they essentially used an artificial spin-ice and put it on a thin film underlayer, and they found that they can tailor the spin wave properties in the film underlay. And this is the approach that I'm going to talk about today. Around the same time, there was work by Adam Papp and George Xaba, where they used a YIG thin film and patterned disks with perpendicular magnetic anisotropy on top of the YIG film. And due to the non-uniform magnetic field, they were able to realize a nanoscale neural network. And then I just want to reference again Will's talk. This is an experimental realization of a 3D magnonic metamaterial based on a tri-layer artificial spin-ice. And Adegunde's group published something similar very recently. Okay, so I'm going to use this pseudo 3D structure. I'm going to put an artificial spin-ice on a thin film. In the first part of my talk, I'm going to show you the field dependence of these kind of systems, and then I will discuss the dispersion. Okay, let's start with the first part. These systems are rather small, so we first put down some alignment markers, which makes it much easier to navigate the sample using optical lithography, E-beam evaporation of Ti gold, and liftoff. And then we use E-beam lithography to pattern our artificial spin-ice network. We use nickel iron in this case. We pattern, or we fabricate 4 different samples. Sample 1 and sample 2 are reference samples. So the first one is just a thin film, 15 nanometers of permalloy. The second one is the artificial spin-ice system, isolated artificial spin-ice, again, a thickness of 15 nanometers. And then we have the two samples, sample 3 and sample 4, where we pattern the artificial spin-ice on top of the thin film underlayer with 2 spacer layer thicknesses of aluminum oxide, 2 nanometers and 10 nanometers respectively. The dimensions of the elements are 260 times 90 square nanometers, and the lattice constant is 355 nanometers. So before I show you the dynamic measurement results, here is some magnetometry, and I'm going to compare here experimental MOAC results with the results of the micromagnetic simulations. On the top, I'm showing here a scanning electron microscopy image, and we're applying here the field in the vertical direction, in the y direction. Okay? So keep this in mind. In red, this is the experimental MOAC data, and in black, I'm showing the results of the simulations. So on the top, we see the film. We essentially see a step-like function. There's almost no coercivity. This is what we would expect from the film. And at the bottom, we see the artificial spin-ice network with three different regions. Region 1 and region 3 are the saturated states. And in this region 2, we see a gradual rotation of the magnetization and the horizontal elements. So imagine first we saturate the system along the y direction, so all the moments point upwards or downwards in the vertical direction. Then we lower the field magnitude, and the moments gradually rotate into their easy axis, which is along the x direction. So this results in this gradual change that we see over here, and then we observe the sudden, abrupt change. This is due to the switching of the vertical elements. Okay, now let's compare this to the hybrid system made of the artificial spin ice and the film. You can see the magnetometry on the right-hand side, and we can clearly now see a new regime here delimited by these vertical dashed lines labeled 4 and 2, and this is when the magnetization and the film are anti-parallel. We can also take a look at the switching fields for the two different spacer layers. So the top here shows the 2 nanometer spacer layer, the bottom shows the 10 nanometer spacer layer, and we can see that the thinner spacer layer features a smaller switching field. I'm showing here 53 and 60 millitesla. This is experimental data. The corresponding results from the simulations are shown in parentheses. So how do we understand this difference in the switching field? Let's take a look at the 2D micromagnetic simulations of the magnetization. On the top, I'm showing the artificial spin ice layer, and on the bottom, the corresponding film underlayer. On the left, we see the result of an applied field of negative 200 millitesla. In this case, the film is completely saturated, and the artificial spin ice shows an onion shape, onion state. And then if we lower the field magnitude to minus 100 millitesla, we see an S state developing in the artificial spin ice. If we continue to increase the field, at some point the film reverses. This is here the case. And if we continue increasing at 60 millitesla, eventually also the vertical elements switch. Now, what we observe here by looking at the different spacer layer thicknesses is that after the film switches, the magnetization texture in the vertical elements is more distorted, and this leads to a situation where the vertical elements undergo reversal more easily, and this explains the lower switching field for the thinner spacer layer. You can also see that we always systematically overestimate the switching field in the micromagnetic simulations compared to the experimental results. And this is due to the fact that we have a distribution of shapes in the experiment which result in this more smooth and gradual change of the magnetization. Now let's switch to the dynamic measurements. We are going to use Brillouin light scattering spectroscopy, which is an inelastic scattering technique. So we can either create or annihilate a magnon. This process is energy and momentum conserving. So we can analyze the inelastically scattered light that carries information about the probe magnons. So we analyze this tiny frequency shift. And if we use a macro BLS system and vary the angle of incidence with respect to the film plane, we can also reconstruct information about the wave vector. We do this in a Damon-Ashbach geometry where the magnetization and the wave vector are perpendicular to each other. So let's take a look at the raw data. So this is the measured anti-Stokes peak at 200 millitesla. On the left, we see the two control samples, film and isolated artificial spin ice. For the film, we only see one mode. This is the Damon-Ashbach mode. On the bottom, we see the corresponding artificial spin ice. It has 3 characteristic peaks, and I will explain them in just a moment. On the right side, we see the coupled system. So this is the film artificial spin ice system with 2 nanometer spacer layer and 10 nanometer spacer layer on the bottom. So by just looking at this, we clearly see that the coupled system has 2 additional modes, labeled here 4 and 5, and peak 1 gets broader. So let's understand this in more detail. I'm showing here the magnetic field dependence. Before I explain the results, let me walk you through how to read this data. The color here represents the BLS intensity, which is a direct measure for the magnon population in our system. Then in yellow here, this is the result of the micromagnetic simulations. And in red, I'm superimposing the results from the mode measurement. So we can correlate the static magnetization with the dynamic measurements. And for this thin film, we can clearly see this Damon-Ashbach character of the mode, and we see a minimum in frequency when the film switches as we would expect. Now on the right-hand side, this is just one spectrum taken at 200 millitesla. We only see one mode as we would expect the Damon-Ashbach mode. Let's take a look at the artificial spin-ice system. The mode spectrum is much richer, so we can see many more modes here. And what is interesting is if you take a look here, this dashed line here, labeled 2, is when the vertical elements switch. And this correlates with this mode switching of peak number 1. So this is associated with the vertical elements. Now we see here 3 modes. Let's take a closer look what those modes are. Peak 1 is the fundamental mode of the vertical elements. Peak 3 here, this is the fundamental mode of the horizontal islands. And peak 2 down there is the edge mode. This gives rise to this characteristic W shape that we see over here with the minimum frequency at these vertical lines 1 and 3. Furthermore, we see here at minus 80 millitesla, we see an avoided level crossing where mode 2 and 3 exchange their character. And at 0 field, we see a mode crossing, so the modes 1 and 3 are degenerate. The reason for that is at 0 fields, in the magnetization in the vertical and in the horizontal elements lie in their easy axis, and therefore the resonance is degenerate. Now let's couple our film to the artificial spin-ice system. So this is the overview. This is what we get, and I'm going to explain this in more detail in a moment. The take-home messages are that the vertical coupling affects the spin wave propagation properties in 2 different ways. The first one is the static interaction, generating a non-uniform internal effective field distribution. And the second one is a new form of interaction, the dynamic interaction, generating a hybridized state between the magnetization oscillations in the top and in the bottom layer. So this is the take-home message. So let's take a closer look and discuss the different modes. So first, I'm going to focus on the modes below the Damon-Ashbach frequency, which is at 14 gigahertz for 200 millitesla field. So we have here peak 2 and peak 3, and another mode at 12.3 gigahertz. And we can immediately see that the modes are uncoupled. So the artificial spin-ice system and the thin film underlayer are not coupled. There is no hybridization. So if modes are below the Damon-Ashbach frequency, the film underlayer shows a negligible response. And if we compare now the dynamics in the artificial spin-ice system in the hybrid system with that of the artificial spin-ice that is isolated, we see that the hybrid system exhibits the same resonance frequency and spatial profile as the isolated artificial spin-ice system. So if you just take a look here, this is peak 2 in the hybrid system, which corresponds to the isolated artificial spin-ice system here, the same for the other modes. So it's as if the film was not there. Now there's a different mode here. This is mode number 4. And here we see that there is some precession, there's some oscillations in the film. This has no nodal lines in the film layer. This is the fundamental mode with a strong localization in the effective field minimum. So it's essentially like a well. And I'm showing here the effective field in this plot here on the left-hand side. And you can clearly see this local minimum underneath the horizontal elements. So the dynamics are basically trapped in this well, and this allows us to excite dynamics even below the FMR, below the Damon-Ashbach frequency. So now what's happening when we go closer to the Damon-Ashbach frequency? So when the artificial spin-ice modes are closer to the film frequency. So we can clearly now see, for example, peak number 5 is a higher order mode in these vertical elements, and they clearly imprint the same kind of pattern in the film underlayer. There's this same kind of spatial profile. This is peak number 1 at 14.8 gigahertz. We see another higher order mode. The same is true in the underlayer. We see this dynamic vertical coupling between the artificial spin ice and the thin film underlayer. And we can also see here for 15.8 gigahertz, this is more like a bulk-like mode. And we can see if we now compare the spatial mode profile between the artificial spin ice and the film underlayer, there is an out-of-phase correspondence between the two. So we can have both in-phase and out-of-phase modes in the system, basically acoustic and optical modes. So this dynamic coupling is a vertical correspondence between the phase amplitudes in the two different layers. So this leads to a hybridization in the layers. I'm not going to show you that, but this effect is robust with respect to the film, to the spatial layer thickness and the magnetic field. So the artificial spin ice imprints its dynamical nodal structure in the film underlayer. So how is the spin wave dispersion now altered by this dynamic mode coupling in the hybrid system? So again, I want to explain first how to read this data. In this case, the color code represents the results of the dynamic micromagnetic simulations. The symbols represent the results of the wave vector resolved BLS measurements. And in this case here for the film, we also fit the experimental data with the Kalinikos-Slavin model. So this is just the Damon-Ashbach mode. So for the uncoupled film, we just see the Damon-Ashbach mode, monotonic increase of frequency with wave vector. On the bottom, I'm showing here the artificial spin ice system. And surprisingly, the modes are rather flat. There is only one mode, and that is the lowest frequency mode that exhibits some kind of variation in frequency. And I'm going to show you this in a little different way. So this are the spectra, different spectra at different in-plane, different angle of incidences corresponding to different wave vectors. And if you look now at this lowest frequency mode, you can see that there is a bandwidth of about 0.5 gigahertz. So now let's compare this to the hybrid system with the artificial spin ice layer in contact with the film through a spacer layer. And we can now see here that the coupled artificial spin ice film system has a monotonic mode above 14 gigahertz, that's peak number 1. And it's partially overlapping with mode number 5. And from both the experiment as well as the simulations, we cannot conclusively tell whether these modes are actually hybridizing in energy. So we see here the indication of dynamic interaction between the two layers, and the modes below 14 gigahertz, below the Damon-Ashbach mode, are only weakly sensitive to the presence and proximity of the film. So just to summarize this, if we are below the Damon-Ashbach frequency, this is here labeled these panels A, B, and C, the modes are uncoupled. You can have a static interaction, that's panel D, here peak number 4, where we have an effective field minimum, a well where the dynamics are localized. And we showed here this dynamic coupling, which is true for peak 1 and peak 5, panels E, F, and G, where we get a dynamic interaction that imprints the nodal structure of the artificial spin ice into the film underlayer. Now, since I have still a few minutes, I just want to show you some preliminary data. So please take this with a grain of salt. So how can we enhance this modulation of the artificial spin ice hybrid system? And the way we thought we could achieve this is by using a material with a higher saturation magnetization to increase the stray field. So we did some experiments. I'm going to show you only the results of the micromagnetic simulations. So we use here cobalt iron boron as the artificial spin ice layer and put this on top of a nickel iron thin film. Previously, everything was nickel iron. So first of all, what we see, or at least tentatively what we see, is that the dynamic coupling is reduced as compared to the all permalloy system. And then we noticed something interesting. There are some modes which are running basically parallel to each other, and they have the same frequency separation. So I'm showing here first the film underlayer, where we see a frequency splitting in the film. You can see this is 11.3 gigahertz, 11.8, 12.3. So they are all approximately 0.5 gigahertz apart. And this leads to spin wave channels in the underlayer, as you can clearly see. So it's independent of the frequency. And in the artificial spin-ice layer, we basically see no dynamics at all. There's something similar happening for the artificial spin-ice system at higher frequencies. Again, film layer here shows basically just noise, but we see a series of almost evenly spaced discrete resonance in the artificial spin-ice layer. And interestingly, this belongs to the same kind of a mode with the same kind of nodal structure. So this is some preliminary data. I want to conclude. I've showed you that we can control spin wave dynamics in a vertical magnonic metamaterial. We combined experimental and numerical studies of this kind of hybrid system made of an artificial spin-ice and a film. The artificial spin-ice facilitates unique dynamics in the film, and we revealed two different interactions: static coupling, which creates a non-uniform effective field, and a dynamic coupling, which leads to a hybridization in which the magnetization of each layer shares the characteristics of the other. And I just want to advertise, we have a postdoc position available on nanomagnonics with artificial spin-ice. So if you are interested, or if you know somebody who is interested or might be interested, please let them know. My email address is mbj@udel.edu. Thank you.